Okay, so this is lecture 6 of electronics 1. It was brought to my attention that you guys already had your midterm, and I wasn't able to get through the full wave rectifier with two diodes and bridge rectifier with two diodes. But the half wave rectifier itself, if you understood it completely, concept's basically the same. The only thing that changes is the circuit topology. So with that being said, it's like if you understood the half wave rectifier, same principles you can apply to the full wave rectifier, the bridge rectifier, and you should be totally fine. And also, line and load regulation with a Zener diode is something that is important. Well, I wouldn't say it's too important. I would just say like it's important to memorize the proof for the midterm. But since the midterm is already passed, I'm not gonna go through half wave rectifier, full wave rectifier. Actually, I did it already. Do half wave rectifier. I'm not gonna do full wave rectifier and bridge rectifier because it's the same concept. You can go through that on your own as long as you understood the video on half wave rectifiers. Line and load regulation is not that important going forward in that class. So just honestly, if you memorize the proof for the midterm, I'd say that's about it. I don't even think it's going to show up on the final exam. With that being said, we've hit 1,000 total views on YouTube, so I'm very, very grateful for that. And I've seen a lot of comments, so thank you very much for all the support, all the comments. It really means a lot to me. And I haven't posted a video in the past week, week and a half. The reason behind that is because of my co-op position. I come home pretty late, and I'm always training. So sometimes it gets pretty difficult for me to sit down, write down my notes, and record. But again, my intention is to help out as much as possible. So this is what I'm doing: help out and keep on helping out for as long as I can. So the plan moving forward would be to go on past the midterm, focus on material that you guys are gonna go through because I feel like the course is about to take a change. Not just I feel like I know for a fact the course is about to take a change. The course is about to get slightly more difficult with amplifiers and transistors because you guys have never ever seen transistors before, and they are three terminal devices. So we're gonna get through that. So let's get started. Again, since you guys never saw transistors before, so what does that mean? It means that you guys are gonna have to go through the semiconductor physics of both the two type of transistors that you guys are gonna see in the course. We have BJTs and MOSFETs. So your professor is gonna go through that semiconductor physics. A lot of derivation is gonna come out of it. Again, you're not responsible for understanding. You gotta understand, but you're not responsible for memorizing all of the semiconductor proofs. So I won't be going through them because I think it's a vivid waste of time. So we're just gonna go through the things like how to actually solve problems. How does a transistor actually work? Okay, why do we need transistors, or why, what they actually do, problem solving, that's actually going to get you the grades on the final exam. So this is my goal, and this is what we're going to focus on. Okay, so obviously go to your lectures, understand the semiconductor physics is going to help you out, but my goal is to give you the practical knowledge. So we're going to start with an introduction to BJTs here. BJTs, well, I should mention the long-term name is just bipolar junction transistor. That's the name of it. So if I zoom in a little bit, we got two types of BJTs. We got the NPN BJTs and then we got the PNP BJTs, right? The name of those basically means it goes back to the semiconductor physics. N for negative negative charges, P for positives, and then N for negatives. Again, you're gonna see that in the class. It's not that important right now. Okay. The thing you need to remember, if we're looking at the NPN transistor right now, we have three terminals. Like remember a resistor right here? You got two terminals. Capacitor has two terminals. A transistor has three terminals. Okay. The one in the middle is called the base. The one with the arrow is called the emitter. And the one with nothing associated with it is called the collector. Okay. And how I remember the difference between an NPN and a PNP is that for the PNP, it starts with a positive. So when you're ejecting inside, that's a positive thing. All right, you always, it's when you're ejecting inside, it's a positive thing. The emitter is pointing inside. That's a positive thing. That's kind of the stupid way that I think about it, but it always helped me out to remember. Okay, and the arrow is always the emitter. So that's one thing to keep in mind. Plus, you might notice here, this arrow actually it just kind of represents a diode. And if this arrow is representing a diode right here, again for semiconductor physics reasons, that means there's a certain VDO associated with that. If you go back to the first lecture, a diode has like a voltage associated with it. So that VDO voltage is the same right here. So this base emitter voltage between the base and the emitter right here, that voltage is going to be equal to the VDO. And that VDO is typically given in the problem. It ranges from 0.65 to 0.85, somewhere in between. But if it's not given to you, you can always assume it's 0.7 volts. Okay? So, excuse me. So a transistor, it's got a couple modes of functionalities, okay? You got the cutoff mode, saturation mode, triode mode, and active mode. For the purposes of this course, we want our transistors to work as amplifiers. So what do you mean by amplifier? You have an input voltage for now. I'm just gonna give you like a very cartoonish definition of that. We're gonna see that in the future. But you're gonna have an input sinusoidal voltage. You want to amplify the amplitude of it. That's your goal with an amplifier. Okay? And for that transistor to work in the amplifier, it has to be in the mode called the active mode. So 99.9% of the time in this course, you want your transistors to be in the active mode so that they can actually work as amplifiers. But now, with your transistors being used in the active mode, comes certain conditions, right? You're gonna have certain conditions. So now, for the NPN right here, the base emitter voltage, this difference right here, for the NPN, it has to be equal to 0.7 volts. Okay, so that's the first condition right here. That's the first condition for the active mode for an NPN. And the collector voltage has to be bigger than the base voltage. So if you go over here, this voltage right here has to be higher than this voltage. So this is the second condition for the NPN. Now notice for the PNP, we have VEB. Now what do I mean by this? VEB is VE minus VB. And VBE would be VB minus VE. So that's the difference in notation, right? From circuit theory 1, we all got that down. We understand these things. So VEB has to be equal to 0.7 volts, which means this voltage difference right here has to be equal to 0.7 volts. And as well, the base voltage has to be greater than the collector voltage for the PNP transistor. Now that we got the active mode conditions knocked out, we're going to go back to the current in those transistors. So in these transistors, you're going to have multiple currents. So now if I can annotate this as we go forward, so this is going to be your base current, this is going to be your emitter current, and then this is going to be your collector current for the BJT. And then this one right here is going to be your emitter current. This one is going to be your collector current, and then this one is going to be your base current. So that's for the PNP transistor. So now the equations, the useful thing about transistors is that if you know one of the current, the equations that are associated with the DC analysis of a transistor is going to allow you to find other currents. In other words, if you know one current in the transistor, you know all of them, which is pretty sweet. So as you can see here, we have IC, the collector current, in terms of IB, which is the base current. Now, where do these equations come from? Semiconductor physics, not going to get into that. It's about how you can use these equations at the end of the day. So beta right here is a current gain, and that current gain is usually given to you when you solve problems, and that number is typically 100. That's the value of beta. It's a constant. So we have IC equals beta IB, so that's equation number 1. And then we have IE, the emitter current, which is equal to beta plus 1 over beta times IC. That's the second equation. And then we have IE equals beta plus 1 over beta IC. So if I take this IC, I plug it right here. So beta IB, replace it for IC. And then I get this equation, which is IC equals beta plus 1 IB. So these are the three main equations for the current that is very important to be memorized, because if you memorize them, you're going to be able to apply them pop, 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 nice and easy. Okay, and I know I've been talking a lot about DC analysis, but what do we actually mean by DC analysis? So when we're talking about DC analysis, what we actually mean is we want to find all the voltages and the currents associated with the terminals of a transistor. So voltage at the collector, voltage at the base, voltage of emitter, collector current, base current, and then emitter current. So if I'm looking at this, I want to find the base voltage, the collector voltage, emitter voltage, base current, collector current, and emitter current. That's my goal. I want to find these things. Why do I want to find these things? Because I want to check these conditions. And why do I want to check these conditions? Because I want to make sure that my transistor is in the active mode. And why do I want to make sure it's in the active mode? Is because I want it to work as an amplifier. So with all that being cleared out, I hope you understand the whole package of the BJT transistor right now. And with that being said, we're going to jump right into an example, because that's the best way to learn. So we're given this kind of situation going on here. Not too crazy. It might look a little bit scary because you got 3 terminals, but trust me, it's not that bad. So we're given that VDO equals 0.7. So what does that mean? As I said before, this is a diode, so the voltage right here is going to be 0.7. The voltage across the base and the emitter is going to be 0.7. as well as I've said before, beta is 100, so it's just a constant value is given to you. So the first thing I want to kind of notice here is I want to find these things, all right? So if I look at what we got going on right here, I can see that the base current is directly connected to this DC voltage of 4 volts. So right away I can go down and write VB equals 4 volts. You don't need a lot of analysis for that, okay? And now I know that the base emitter voltage, VBE, if I look at the conditions of the active mode right here, well, VBE has to be equal to VDO, which is 0.7. In our problem, VDO is 0.7, sweet. So that means this voltage difference right here, VBE, which is VB minus VE, that has to be equal to 0.7, and that's exactly what I wrote down right here. But guess what? I already know what VB is. VB is 4 volts. So my equation right here is 4 minus VE equals 0.7, where 4 is just VB, okay? I'm just applying the equations right here. And from that, I already get my second answer that VE equals 3.3 volts. And mind you, VE is the voltage right here, which is the emitter voltage. Now, I have the emitter current right here. But guess what? I know the voltage and I know the resistance. What does that call out for? That calls out for Ohm's law, right? So IE, where is it? I think I wrote it here, right? There we go. So IE is going to be VE minus 0 over the resistance that we got here. That's just Ohm's law. So I plug in my value for VE over the resistance and I get that IE is 1 milliamps. Now, as I've said before, the moment you know one current inside of your transistor, you know all of them for free. So all I have to do is use these equations to find IB and IC. Easy work. So IE, if I look at this equation, is beta plus 1 over beta IC. So what is beta? So I have here. The thing is I already know what IE is. I'm looking for IC. So I use this equation, I isolate for IC, I replace my beta by 100, and then I get what my IC is. No need to go into crazy details. Actually, very, very simple if you understand these equations, if you understand the voltages and everything, and you apply the conditions. Okay. So now I know what IC is. Okay. But now if I look up, I know that IC is equal to beta IB. So IC equals to beta IB, which means that IB would be IC over IB. So again, I put my replacements right here and I get my current right away. So IC is equal to this thing. So now I know what base voltage is, emitter voltage is. I know all my three currents. The only thing that I don't know is the VC, which is the collector voltage. So how do I do this? Again, this is what I need to find a voltage. I know the current and I know the resistance. That calls out for Ohm's law again. So I have that IC is 10 minus VC over 4700. Where do I get that from? This current right here is going to be the high potential minus the low potential over the resistance. That's just Ohm's law. So then if I look at this equation, well, IC I just computed right here, okay? So I can isolate easily for VC, so that's what I do. I isolate for VC, I plug in my value for IC right here, and I get my VC value. Easy, nice and easy work. So this is a very, very easy example of a BJT transistor. I recommend that you actually kind of pause the video and then go through it yourself and try to solve the problem. I should have said that before, but it's fine. This is your first. You can pause the video and go through the math and then the calculations yourself here. Okay, this is a very easy example. Now we're going to move on to a more complex example and sort of the examples that kind of repeat itself throughout the course uh, totally from now on. Because as I've said, we want to keep our transistors in the active mode, right? And one way to keep the transistors in the active mode is by using a resistive network. What do I mean by resistive network is just like at the base of your transistor, for example, here, we're going to have some random like combinations of resistors here just to make sure that the conditions of the active mode are held properly. So we're given this kind of situation going on here, and all of the values that you see here, VDD is equal to 12 volts, RB1, the values right here, RB2 here, RC is here, and RE is here, okay? And then beta is here. Now, understand one thing. The moment your base is connected to some sort of resistive network that sort of look a little bit complicated, we have to use Thevenin. Obviously, you can go ahead and apply a KCL right here, whatever you want to do, but it will take you a while. And that while we don't have in an electronics exam. You need to be working fast. and you need to be working right away. So we want to use the methods that give us the answers correctly the fastest. So this is what we're going to do. So I've kind of highlighted this in orange right here, and I've called it the resistive network. So if you look at this arrow right here, so I want to replace this resistive network pointed by the tip of the arrow, and I want to compute a Thevenin equivalent circuit as pointed by the arrow. So what do I mean by this? If you look over here, we have a graphical representation of this for the people that are more visual. So we got this kind of situation. We have this, which is drawn right here. So I want to replace this with this. And this is the Thevenin equivalent circuit. Notice here, I have a voltage source and I have two resistances. In this case, I have one voltage source and one resistance. Much easier to deal with. Okay. The thing is I just want to find the value of VOC and I want to find the value of R Thevenin. How am I going to do this? Well, if you remember from circuit theory, you're going to apply open circuit voltage VOC to the terminals you're actually interested in. You're going to compute the value of VOC. So that's exactly what we're going to do. So this is the situation here. This is the circuit. So I'm going to apply VOC right here. So that's what I drew right here. At this terminal and this terminal, I'm applying my VOC. And remember, VOC is an open circuit. So since in an open circuit, I equals 0, there's no current going through here, no current going through here. So whatever current you got going flowing down here is going to be flowing through this resistor as well. And now if you got the same current flowing through both resistors, it means that these two resistors are in series. And if these two resistors are in series, that means I can apply the voltage divider. Voltage divider would just tell me that VOC would be RB2 over RB1 plus RB2 times VDD. That's just voltage divider from circuit theory 1. And right away, I already have my VOC value. Because everything here I know. Okay? I know what VDD is, I know what RB1 and RB2 is, so light work. So the moment I found my VOC, now the thing is I need to find my my R Thevenin. And if you remember from circuit theory 1, when you already have your Thevenin voltage calculated, the way you would find your Thevenin voltage is by disabling all the independent sources. So that's what I'm going to do here. So over here you have an independent source VDD, so I'm going to disable that and just going to be ground. So this is what I got going on here. And now if you look at the situation here, this point is the same for RB1 and RB2, and this is ground and this is ground. So RB1 and RB2 are also connected to each other right here. You can kind of imagine it this way. So here is a common point and here is a common point. So that means these two are going to be in parallel. Okay. One more way I can draw this is sort of this point. I want you to picture this point right here, and I extend it. This is RB2 connected to ground, and then I'm going to draw this part right here. This is RB1 connected to ground. So these two are in parallel, okay? So R Thevenin would be RB1 parallel with RB2. Now, the known values are here. You have this equation, you have this equation. If you plug in the numbers, these are the numbers that are going to be spit out to you. So VOC is 3 volts and R Thevenin is 7,500 ohms. So now, okay, we wanted to replace this thing with this thing. And guess what? We already found the values of VOC and RTH. So our circuit, everything here stays the same. It's just that the circuit over here, we replace it with our Thevenin equivalent circuit. Okay? So this is what we got going on here. We replace this part with this. And it's still connected at the base. Okay. So now just this is my open circuit voltage VOC. This is my Thevenin resistance, and this is my collector resistance and my emitter resistance, and the values are given here. So this is what we got going on. And now one word of advice is like the moment you finish your Thevenin, right away do a KVL right here. Go for it. Just do a KVL right here. Trust me, don't even think about it. Just go for your KVL right away because it's the fastest way to get through these things. So if I do a KVL right here, I got minus 3 volts, which is here, plus 7,000 times the base current, because I'm in the base right now, times the base current, 7,000, 7,500 times the base current, sorry. And then over here, I can't forget that I have plus here, I have VBE. All right, VBE is the voltage drop across this diode right here. So I need to consider that as well, plus VBE, and then plus this resistance value, 1300, times the current going through it, which is IE. Be very careful. It's not going to be IB because this is the emitter. The only way you could mess up in this sort of situation here is by getting your currents wrong. You have to make sure you look at your terminal that you're working with and make sure you're staying consistent with that. So I'm going to go through that one again. Minus 3 plus 7500 times IB because I'm in the base, plus this voltage drop, VBE, plus 1300 times IE because I'm at the emitter. And this is my equation. And all of that is equal to 0, of course, KVL, everybody knows that. So VBE is equal to 0.7. Why? VBE equals 0.7 is one of the active mode conditions. It has to be equal to VDO, which is the voltage across the diode. So VBE is equal to 0.7. So I just take that in and I plug it right here. So my equation simplifies to this. And now this minus 3 and the 0.7, I can combine it here. And the only thing, if I look at this equation here, is I have two unknowns, IB and IE. But are there really two unknowns? Well, no, not really. Because once you know one current of your transistor, you know all of the currents. So all I have to do is play around with these equations so I can express one current in terms of the other. And then my equation would have overall only one unknown. And I find that current. So that's what I'm going to do. Well, what do I got going on here? So here, okay, I have this sort of this equation here. I know that IB is 1 over beta IC, okay? And I also know that IC is beta over beta plus 1 IE. So now if I want to find IB in terms of IE, so I have one unknown, I should take this IC value here and I plug it in this equation. So I do that. IB is 1 over beta times this thing, which is IC. Okay, so these two betas are going to cancel out. So I have IB is 1 over beta plus 1 IE. But beta is 100 plus 1 is 101. Okay, so this is the equation for IB. Now I have IB in terms of IE. So I take that, I plug it in this equation right here. So minus 2.3 plus 7500 over 101 times IE plus 1300 times IE. And this is equal to 0. If you look at this equation now, you have only one unknown, which is IE. All you got to do is isolate for it. So here I just factored IE out, multiplied by this constant value. I took my 2.3, sent it to the other side, and then I isolated for IE from this equation, and then you just plug in your calculator and you get this value IE. Okay, so we know what IE is. Now, IE is equal to this value, you just plug in your calculator. Okay, but now as I said before, the moment you know one current in your transistor, you know all of the other currents. So this is my value for IE. Now, I know that IC is beta plus 1 over beta IE. Now, where am I getting these equations? Just at the top of the lecture, right? At the very top. All right, here, let me show you again. There we go. These are the equations, okay? I'm just using these. Excuse me. So IC is beta plus 1 over beta times IE. Again, beta is 100, so I have 101 over 100. IE's value, I just computed right here, so I take it and I plug it right here. And it spits out the value for IC. And then from here, I know that IB is IC over beta. Again, I take my IC value, put it right here, divided by beta, and I get IB. Easy work, easy work. All right. If you get your Thevenin right, you do your KVL right, everything is fine. What we're noticing right here is we have a transistor. However, the circuit theory remains the same. So it depends, it really depends on how good you are at your KVL and KCLs. If that's a little bit shaky, go back, watch, go back to your circuit theory and practice more. And if you want kind of a fast track to your circuit theory to make sure you got everything going on here, because going from here and to the final exam, from this point on to the final exam, is gonna be a lot and a lot of circuit theory. So if your circuit theory is shaking, make sure you brush up on those. It's very important. I can't stress this enough. And if you want a faster way to kind of brush up on your circuit theory, I do have the cookies and cram. The first video I ever posted on this YouTube channel. It's 2 hours long. You can get through it, and it's like a crash course of circuit theory 1 totally. It will help you out throughout this course. So you can do that as well. So where was I? We calculated all over 3 currents. Now we need to calculate all over 3 voltages. Now if you look at this IB here, right? Well, I know what this voltage is. Okay, and I know what the current is, IB. So that means I can find my VB. I can apply Ohm's law. So what do we got going on? Where is it? So IB is going to be 3 minus VB over the resistance 7500. So high potential, I got current flowing this way, IB. And this IB will be equal to the high potential, which is 3, minus the low potential, which is VB, over the resistance 7500. Okay, So this is this. Okay, IB, I know the value, and I just isolate for VB here. So I plug in my value here, isolate for VB, and this is my answer. Okay, if I go back here, VBE, well, that's VB minus VE, all right? And VB, I just computed this value, 2.87. So it's 2.87 minus VE, right? But this VBE has to be equal to 0.7. So this is my second equation. I have 2.87 minus VE, and this is equal to 0.7. This is my other equation. I can easily isolate for VE from here. So this is what I got going on. VBE is equal to VB minus VE, which is 0.7. However, VB I already know. It's right here. I plug it in, and all I need to do is isolate for VE, and boom, I got my value. So I got my base voltage, I got my emitter voltage. Now the only thing I need to find is my collector voltage. Again, as you can see also, like, once you find all the currents and the voltages, I'm just using Ohm's law. There's no crazy KCL, KVL. I'm just basically using Ohm's law. All right, no phasors, no nothing like that. Okay. So this IC right here, okay, I can use Ohm's law again. This current is pointing down, so it's going to be high potential VDD minus low potential over the resistance 4300, okay? VDD is 12 in our case. So IC would be 12 minus VC over 4300, okay? 12 minus VC over 4300. So I isolate for VC because I know what IC is. The value is right here. I plug it in, I isolate for VC, and this is my value. Nice and simple. So now I have all three voltages and I have all three currents. What do I need to do? I need to check the active mode condition, all right? And if I look at the things at my transistor here, all right, my emitter is pointing out. It's not pointing into my transistor, so that's a negative thing because you're pointing out, all right? That's a negative thing. So we're dealing with an NPN transistor. What would now that we know when we're dealing with an NPN transistor, we'll look at the conditions. First, VBE has to be equal to 0.7. So let's check that out. VBE is VB minus VE. What is VB? It's 2.87 and VE is 2.17. I plug it in, it's 0.7, double check, very nice. What's condition number 2? Condition number 2 is that my collector voltage has to be greater than my base voltage. Let me check this out. Collective voltage is 4.73, base voltage is 2.78. Of course, 4 is greater than 2, so this condition is checked out. Hence, my transistor is in the active mode, so we can accept this mode of operation. So that's basically it. And honestly, go through these examples yourself. Make sure you get the answer correctly. And then if you're not getting the right answer, go back to the video. Just watch the parts that you actually really need. Honestly, that's it. It's not too bad. It's not too bad. BJTs, transistors are not too bad. They're just very, very scary. And I think people assume for them to be very scary in analysis because how complicated the semiconductor physics actually is. So if you can detach yourself from the semiconductor physics and the actual circuit, I think that you could benefit a lot from that. Just understand how to solve problems. You're gonna have a whole course in semiconductors. Worry about it then. For now, solve problems and get your A plus. That's all I can give you. And again, share the videos, Max. I appreciate the support. Um, we're gonna have more videos in the future. Amplifiers, I love them. I, so we're gonna have a lot of fun with those. With all that being said, if you want to see more content from an unconventional small YouTuber, hit that subscribe button. Maybe leave a like and a comment if you like me enough. All right, have a good day.